Hello everyone, today we're going to look at volumes of solids of revolution using the shell method. We're going to use the shell method in this lesson about different vertical and horizontal lines that are not the x or y axis. We'll start with the y-axis. Let's review. Suppose region R is bounded by y equals the square root of x equals 9, and the x-axis. And I sketched those for you, and the intersection points here are 0, 0, and 9, 3. Okay. Now, we would like to set up an integral to find the volume of the solid of revolution if this region, the yellow region, is revolved about the y-axis. Okay, so with the shell method, recall that the rectangle is parallel to the axis of revolution. So in this case, we would use a vertical rectangle. And notice that the coordinates here are x comma 0 and x comma root x. So the distance from the y-axis to any of these vertical rectangles, no matter where they're drawn, will always be x. And that's very important for the shell method. We have to remember that the distance from the y-axis to any of the vertical rectangles is x, that horizontal distance. The height of the vertical rectangle is just top minus bottom, or root x minus 0. Right? Okay. So if we're going to form a shell here, we would reflect here. And we see that the radius of the shell is x. When we go around the y-axis, the radius of the shell will be x. So our formula is 2 pi. The x limits of integration are from x equals 0 to 9 of the radius of the shell times the height of the shell, and that's top minus bottom. So that's root x minus 0 dx. We did this in the last lesson. All right, now what happens if we go about a different vertical line parallel to the y-axis? Let's say x equals 9. So I'm going to erase this. I don't need this. Okay, I'm going to erase this. And x is still the same here. The distance from the y-axis to any rectangle is x. But now we're going around this line, x equals 9. Actually, I'm going to write this a little lower. I'm going to put it down here. So we're going to go around this line, x equals 9. I'll put that in blue because it's part of the region. Okay, now note that if we're going around to the right, this yellow region is going to be reflected over to the right. This vertical rectangle will be reflected here. And notice that the shell is off to the right. So we can't say that the radius of the shell is x. It's something else. Notice that the radius of the shell is this distance or this distance, right? This is the radius of the shell. However, the height of the shell is the same. It's still top minus bottom. It's unchanged. It's the radius that changes, which is the beauty behind the shell method. Well, the key here is to always consider the distance from the y-axis to the axis of revolution, and that is 9. So the radius of this shell would be 9 take away x. So our integral would be now 2 pi on the outside. The limits of integration are still the same, but the radius is 9 minus x, and the height of the shell is still top minus bottom. All right, Now let's look to the left of the region. Suppose we revolve around the vertical line x equals -1, which is over here. And we go around this way. All right, well, keeping the same vertical rectangle, we have a bigger gap between the x equals -1 and the rectangle. So the radius would be from the axis of revolution to the rectangle. So I have to leave a big gap, and we've got a shell, a very, very wide shell, going this way. Okay, now notice that here, the radius of this shell is here. It's always from the axis of revolution. So this is the radius of the shell. So the radius of the shell is more than just x. X is here. We have to take into consideration this distance, which will always be 1. The axis of revolution to the y-axis is 1, just like the other axis of revolution, x equals 9, to the y-axis was 9. So in this case, the radius of the shell would be x plus 1. So let's write it down. 2 pi, the definite integral from 0 to 9 of x plus 1 times the square root of x minus 0. And that would set up the integrals if we had vertical lines, if we're going around vertical lines that are not the y-axis. Notice I have a situation where the vertical line was the boundary of the region and the vertical line was to the left of the region. What would happen if the vertical line was to the right of the region or in between the region? So let's take a look at these two examples. Okay, so I redrew the region this time, and we're going to go and revolve the yellow region about the vertical line x equals 12, which is 3 units to the right of x equals 9. So this is the axis of revolution, and I'll put a little arrow here to indicate it. So we still have a vertical rectangle in the yellow region, the same vertical rectangle. This distance is still x, and the distance from the y-axis to the axis of revolution is 12. Okay, so we always find the distance to the y-axis. Now, when we revolve this green rectangle about this vertical line, the radius of the shell will be here. And we'll see it when we draw the shell. So I have a big gap, another big gap. So the vertical line appears here. When I reflect it, and then I've got a huge shell going that way. Notice how the height of the rectangle doesn't change. It's just the radius of the shell. So let's put it together. It's still 2 pi, the definite integral from 0 to 9. Now, the height of the shell is still root x minus 0. That doesn't change. But how can we represent the radius of the shell? Using x and 12. That's the idea. Using the distance x and the distance of the axis of revolution to the y-axis, we have to represent the radius of the shell. And it looks like it's 12 minus x. And that would set up the integral. Okay, so we looked at the scenario when the axis of revolution is on the right of the region. We looked at the scenario when the axis of revolution is on the left of the region. What would happen if the axis of revolution is somewhere between the region and the y-axis? Okay, because here we looked at an axis of revolution to the right of the y-axis, but to the right of the region as well, and to the left of the y-axis, to the left of the region. But what happens if we translate our region 2 units to the right and get this graph? Note that the volume should not change because we're revolving the same area. But this time, we're going to revolve this region about the vertical line x equals 1. Oh, let me just get that vertical line in there. X equals 1. Oh, have to perfect my vertical lines here. All right, so x equals 1, somewhere in between here. Right there. So I have to draw a vertical line there. Okay, that's good enough, I guess. All right. So now remember, here is our vertical rectangle. Of course, the functions will change here because they bound different curves, all right? And this distance will still be x from the y-axis to the vertical rectangle. This distance is 1 from the axis of revolution to the y-axis. And when we revolve this vertical rectangle about this blue line, the radius of the shell will be here. Okay, I'm going to outline it in red here. This is the radius of our shell. So, okay, so we have this, we reflect over. I just want to make sure it's symmetric. Oh, gotta get my pencil going here. So symmetric. And we got the shell going this way. Okay. All right. So now the question is, how can we represent the radius in this case? Well, in this case, let's start writing up the integral. So it would be the volume of this solid when we revolve around the vertical line x equals 1. Okay, 2 pi would go on the outside. The x limits of integration would be from x equals 2 to x equals 11. And now we have the radius, but the height of the shell is square root of x minus 2 minus 0, top minus bottom. The radius of the shell would be x. Notice x is larger than the distance of the axis of revolution to the y-axis. So that would be x minus 1. And that would take care of the scenarios. All right, so can we discuss a shortcut on how to get the radius of the shell when we go about a vertical line? Well, let's think about that. All right, so we have the shell method. With respect to x, the height of the shell will always be top minus bottom. Top curve minus bottom curve. To find the radius, okay, let's see if we could put it together and make a formula out of it. So there's a way to figure out the radius of the shell, which is really the key. Let x equal k be the axis of revolution. All right, so we've got 3 scenarios, and I'll abbreviate axis of revolution as AOR. So if the axis of revolution is negative, that is to say, it's on the left side of the region, but on the negative side, okay, so if the axis of revolution is less than 0, then we could say that the radius is x plus the absolute value of k. And this was illustrated on the previous page when the axis of revolution was x equals -1, then the radius was x plus 1, where 1 was the absolute value of -1. If the axis of revolution is on the right of the region, we could just say greater than or equal to the upper limit of integration. Then the radius is equal to the absolute value of k minus x. And we can see that in problem number, part D, where the axis of revolution was 12 or 9, we saw that the radius was the absolute value of 12 or the absolute value of 9 minus x. But the tricky part is when the axis of revolution is between the lower limit of integration and 0. Okay, so that was the second one, the second problem. And we saw that in this case, the radius is equal to the absolute value of k. I'm sorry, it's equal to x minus the absolute value of k. However, I think it's just as easy just to sketch the axis of revolution, see where it's located, identify the distance x and the distance of the axis of revolution to the y-axis, and it's very easy to figure out the radius of the shell. Okay, now let's take a look at the shell method going about horizontal lines. The first one is our classic, when we go around the x-axis. And when we go around the x-axis, notice that the x-axis is horizontal, so we have to draw a horizontal rectangle to get the shell. And the same is true in B. If for y equals 3, well, let's just see where that is. This is 9, 3. 9, 3. 9, 3. So in the second problem, our axis of revolution is right here at y equals 3. Y equals 3. Here in the next one, our axis of revolution is a little above the region, y equals 4. But each of these are parallel to the x-axis, so each of these require the same horizontal rectangle. And if you recall, with a horizontal rectangle, we integrate with respect to y in each of these cases. And the height of this rectangle is always right minus left. So we could start setting up these integrals. Let's do that. So outside, we've got a 2 pi in each of them. Okay, I didn't do the last one, but we'll look at that later. And the y limits of integration are from y equals 0 to y equals 3. Okay. Now, the height of our shell will always be right minus left. So the right is x equals 9. The left is x equals y squared if we isolate the x. Okay. Oh, sorry, I wrote the wrong variable there. Let's just erase that quickly and make that a y. Okay, but how do we get the radius? All right, so again, let's visualize. When we rotate this the first horizontal rectangle about the x-axis, we've got our shell going this way. The radius of the shell is this distance from the rectangle to the x-axis or the axis of revolution. And remember, these 2 points can be represented in 2 ways. This point can be written as y squared comma y, and this point can be written as 9 comma y. So we notice that the radius of our shell is this height, which is y. So here the radius of the shell is just y. And the radius of the other shells will be something with y. We will either subtract or add the axis of revolution. So let's look at the others. When y equals 3, we're rotating the horizontal rectangle above. So the radius of the shell is here, or this. So we know that this distance is always y. The distance from the x-axis to the rectangle is always y. The distance from the x-axis to the axis of revolution is 3. So the radius of the shell, which is above that, is 3 minus y. And we could use the same idea as we had last time. Okay, now when y equals 4, all right, we're moving up 1, so we have a bigger gap. So again, this distance is y. The distance from the axis of revolution to the x-axis is 4, so the radius here would be 4 minus y. Okay, in the next problem, we have a line below the x-axis, so let's quickly sketch it. Y equals -1 is 1 unit below. Our rectangle is still horizontal. And remember that the distance from the horizontal rectangle to the x-axis will always be y. Well, let me put that in red. This is y. The distance from the x-axis to the axis of revolution is 1. And so when we rotate this rectangle about the horizontal line y equals -1, the radius of the rectangle will be here. That's the radius. And if we're not sure, we could always do the rotation and see. Remember, the axis of revolution always goes through the middle of everything, whether it's a washer or a shell. So we see that we can write the integral here, 2 pi, 0 to 3, but the radius is y plus 1 times 9 minus y squared dy. And this is consistent with the rules that we had last time. If the axis of revolution is less than 0, like in the last one, it's y plus the absolute value of k. If the axis of revolution is greater than or equal to the upper limit of integration, then the radius is the absolute value of k minus y. And of course, the last situation, I don't have it, but we could easily create it. When the axis of revolution is between 0 and the lower limit of integration. So let's look at that at the next page. So I wanted to show you the shell method when we revolve around vertical axis of revolution other than just the y-axis. So if we revolve around the y-axis, we already saw that this vertical rectangle becomes a shell. So let's revolve it. And we see the solid form. Okay, and we're summing up the volumes of all these shells. All right, now, and if we sweep the shell, we see that we sweep it and we're summing up the volumes. So it looks like a cylinder with a cone in the middle and it's empty. All right, now I'm going to move the axis of revolution and I'm going to move it a little bit to the left. Now, as we revolve this blue region around the axis of revolution, what really changes about the shell? So let's sweep the shell, okay, and revolve it. Okay, let's just stop sweeping it and we'll revolve it. So notice that it looks like the height of the shell is the same, but the radius has changed. The radius is just affected when we change the axis of revolution. Okay, let's just reset this now. And now we're going to move this axis of revolution to the right of the region. Okay, like there, or even here on the boundary. And we revolve this vertical rectangle. Notice we get what looks like, well, I can't say it's a lampshade. It looks like a lampshade on the outside, but on the inside, it's a hollow cylinder. Okay, and we could sweep the shell. We could see that we sum up those volumes. And again, the height of the shell is unchanged. It's the radius that changes. So let's reset that. And let's move the axis of revolution a little bit further to the right. So there's a gap between the axis of revolution and the area of the region. We'll revolve this. Okay, let's see if we could move this over a little bit. Yeah, so we need more room. We'll revolve the rectangle around this vertical line. And notice that this is a cylinder that has a much wider radius. And we could sweep the shell. Notice there's a hollow cylinder in the middle. And that this is a nice visual just to emphasize the fact that the height of the shell is always f of x. It's the radius of the shell. We have to adjust the x. The distance x is from the axis of revolution to represent this distance or the distance to the left. Okay, that takes care of our
lesson
demonstration.
on shells for today, both in terms of X and Y. Have a wonderful day.